Welcome everybody to episode number 2 of my Amiga game development series that I've been doing. Episode number 2. I'm really over the moon with which way episode number 1 went. I've had loads of likes on the Facebook page. I've had lots of people following the series. So I thought I'm gonna try doing this on a weekly basis. But actually this week has been really quite difficult. If you've got kids, you'll know in the UK that some of them have been off this week and possibly the week before. So I've kind of been in that camp. And yesterday was Halloween, so I didn't have any time to do anything really for the past few days due to having prioritising on family type stuff. Which is absolutely fine. But here we are, Friday night. I've got the house to myself. I've got a beer in hand as well. I'm on the Moretti tonight, and I've got a nice episode coming up where we're going to touch on some things and actually get into a little bit of practical coding, which should be good. So I've kind of updated the slides a little bit, the master slides. What we've got here is just to make people aware, I've registered a domain, AmigaGameDev.com. You can go there to find the episodes of the tutorials. I've also got a Facebook page, which I've got the link there, and I've also got a Discord channel as well that people can join and have a chat with me and other people that's following the series. And if you want to ask questions, go there or on any of those links. You'll find me kicking around there. So onward with episode 2, Byte Basics in the 68,000 CPU. I know the titles are not that great, but I've just got to come up with this stuff pretty quickly as time passes quite quickly as well. So we're going to get right into it. This is what I've came up with for this week. Episode number 1 recap and clarifications. Some people responded back on episode 1 with some things that I need to just maybe clarify or where I've said possibly the wrong thing or not given the right advice. I just need to clarify. We're going to look at some numbering systems which are really important, binary, hexadecimal, which are important to computers. We're going to do a quick Boolean logic primer. We're going to look at some common assembly instructions. We're going to take a look at the Amiga CPU, which is pretty important given that we're doing assembler and game coding on an Amiga. We're going to put some instructions to the test. That means we're actually going to do something practical there. We're going to look at MONAM basics, which is my debugger of choice. I really love MONAM, and hopefully you will too. And we're going to look at something called tri-states, which is when you're doing game development. I kind of found that I was doing this all the time, and I found it was really pivotal in everything I was doing. It's a really nice starting point to work with from an assembler point of view, and just to kind of ease you into learning a bit of assembly language, and it really gives a good kind of steer on working with the CPU and in particular the status register, where we'll come on to it. We're going to look at labels, branches and subroutines, and then we'll do a wrap up as well. So cool, here we go. So quick recap and clarifications of episode 1. So in episode 1 I covered the tool chain and how to set up the tool chain, and the idea behind that was to use a modern dev environment rather than actually doing the coding on the Amiga. What you essentially do with the tool chain is you put the tools on your host operating system like Windows 10, and you do your coding on Windows 10, and you have WinUAE or FSUAE running also on Windows 10, and you do your assembling on the host operating system and copy the binary into the emulated Amigas that are running on the emulator, either WinUAE. So in essence, we're developing in Notepad++, we're assembling with VASM, and we then do our build. Once we've assembled, we actually run the assembled programs on these kind of hard drives that we have set up in WinUAE. And it's really that straightforward. I gave a really good example of it in the previous episode. So that was the whole kind of purpose of that episode, is getting that up and running and making that work. So if you haven't gotten there yet, I suggest that we kind of go through that. If you've got any questions, find me on Discord. I'm also on the EAB quite a lot, and I can certainly help you get that up and running. Not a problem. Okay, so numbering systems and counting like a computer. So what have we got? Most people, if you do a count, work on a numbering system called base 10. Now, base 10 is typically how you count in the decimal system: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and so on and so on and so on. Basically, everybody learns it. Learn to count. For example, my 3-4-year-old, he's learning to count base 10 at the minute, counting all of his numbers up to 20, 30, 40. Really important if you actually want to get on in life, I guess, to learn that. However, computers don't typically work on base 10. Computers like something called base 2 or binary, which is essentially just either on or off, 0 or 1. Computers work like that. They work in binary. The CPU inside a computer will only actually only recognizes binary numbers, 0 and 1, and you feed enough of them and it makes the computer do various different things. Now, to make things a bit easier for the computer, we typically convert the the assembler that we create is then turned into hexadecimal, which is put into the binary of a file. And hexadecimal is typically what we'll be using and getting very familiar with, rather than the binary. And the hexadecimal is called base 16, and in computing terms, where we go from 0 to 10, we will go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and instead of going to 10, we go to A. And for 11, that is B. For 12, that is C. For 13, that is D. 14, E. 15, F. And then 16 goes back to 10, and so forth. And then it carries on, keeping on going all the way up like that. So that's called base 16. So before you get to the next double digit, you get, the 16 numbers. So 0 through to F, and then you get your double digit 10, which is 16, and so forth. That's the idea. So we're going to just look at some numbers from base, what would be in base 10. So 165, we're going to take that number. In binary, it looks a bit like that. I'm not going to go through why it is that like that, but we're going to explain how it is like that. In base 16 or hexadecimal, it is A5, and that is just what it is, and we'll work it out in a few short moments. So, important points: a byte contains 8 binary bits. A word contains 16 binary bits. So when we talk about a word and 16-bit systems, that is typically a word. So a word is 2 bytes. And then we've got a long word, which is 32 bits. And we've also got something that you might not have come across, which is called a nibble, and that is 4 binary bits. So that's kind of half a byte. And we'll look at those as well. A couple of other things that I should mention, that I might mention later on, is MSB, most significant bit, and LSB, least significant bit, which are quite important when we're dealing with this sort of stuff. Boolean logic primer, Nybbles, Bytes, and Hexadecimal. So we're going to take this byte effectively, and at the top here we've got the 8 bits of a byte, and the first bit, which is bit 0, is called the least significant bit. And we've got all the bits at the top here: 1, 2, 3, 4, 5, 6, 7, and bit number 7 is called the most significant bit of a byte. Now, the most significant bit of a word would be bit 15, and of a long word, that would be bit 31. And it's called the most significant bit because it has the largest value. Okay, and in this case of a byte, bit number 7, which is the most significant bit, has a value of 128 in decimal. that is base 10, or call it hex 80, which is 128, hex 80 in hexadecimal. And as we go down the bits within the byte, you'll see this works on a power of 2 system. So if we go to the first bit, we've got bit 0, which amounts to 1, and then we go to the second bit, which is 2, and then it doubles again for the third bit, which is 4, it doubles again for the fourth bit, 8, 16, 32, 64, 128. And that's essentially what makes up a byte, okay? And each bit, as we said, is base 2. The bit can either be 0 or 1, and so it can be on or off. So in this case here, we've got this byte, we've got bit 7 is switched on, we've got bit 5 is switched on, bit 3 is switched on, bit 1 is switched on, bit 0 is switched on, so that will be 128 plus 32 plus 8 plus 2 plus 1 equals 171. In hexadecimal, that equates to AB. Okay. So just going to look at the nibbles now, and a quick way of working out how we get to actually AB. Okay, so taking those bits that were actually switched on, we can see here that if we take the 2 nibbles, so we take the rightmost nibble first, so bit 0, 1, 2, 3 of the rightmost nibble, we can see 1 and 2 and 8 are switched on. Now that is quite easy to calculate up. That is 11, and 11 in hexadecimal is B. And for the leftmost nibble, we've got 2 switched on and we've got 8 switched on, and that is 10 in decimal, which in hexadecimal is 8. So that is why we get AB, 8 plus 2 upper nibble. So 8 plus 2 here is equal to 8 in the upper nibble. Sorry, I call them the upper nibble and lower nibble. And 8 plus 2 plus 1 in the lower nibble is B. So the answer is AB. A really good thing which you'll actually come on to as you do some development. You often come a time when you need to work out whether a number is actually odd or even, and the real easy way to work that out is that you just check the least significant bit. If the least significant bit is actually set to a 1, it means that the number is odd. If it's off, it is even. It is simple as that. The least significant bit always adds the 1, the odd number. So we're just going to look at some Boolean logic primer now, and an OR. I appreciate that, you know, this is kind of really going back to the basics of computing, and you know, if you know this stuff, feel free to fast forward on. You know, I'll not be offended, but you know, people might need a refresher, and you know, it's worth me kind of going through this just for completeness of the series. So we're just going to look at the Boolean logic primer of and OR. So and works like this. So given that we have 2 bytes here, okay, and the first byte, as we know, is AB, and the second byte we've set to FO, okay, and we want to know what the result of that is. So if we take and we take value 1, which is AB, and it with value 2, which is FO, the result of that will be A0. Now why is that? Well, let's have a look at the bits, okay? If we take a look at value number 2, which way and works is, it says, right, if the bit from value 1 and the bit from value 2 is true, i.e. they're switched on, so they're a 1, then the result of the bit will be a 1. If value 1 and 2 are different, so they don't match, one's a 0 and the other, or vice versa, the result will be a 0. So let's go down this. So bit 0, so we've got value 1 is a 1 and value 2 for bit 0 is a 0. Well, those are not the same, so the result is a 0. And similarly, that's the same for 1. Now we've got bit 2, which is a 0 and a 0, so that is going to be a 0. Bit 3, 1, 0, 0. Bit 4, yep, we don't have 2 positives there. But bit number 5, as you can see here, value 1 and value 2 are switched on. So the result there on the AND is that it is switched on. Bit number 6, we've got a 0 and a 1, that means it's a 0. And bit number 7, the most significant bit, value 1 and 1, value 1 is 1 and value 2 is 1, that means it's a result of 1. So therefore we can then calculate the value of the result as being A0. Now when you're working with assembly, you find you need to do this type of thing, typically what's called masking off bits all of the time. You know, I do it a lot, I've done it a lot in my games. You tend to need to be able to mask off certain bits or do things like that, or shift things around in bits. So that is kind of a real simple, that's a real good example of needing to do that, so using AND to mask off bits, so setting all bits in a byte to a 0. OR works like this. OR works that if the value of 1 is a 1 or the value of 2 is a 1, then the result will be a 1. Okay, so let's run through that. So bit number 0, the least significant bit, we've got a 1 in value 1. That means the result is a 1. It's as simple as that. We've got the same for bit number 1. Now bit number 2 is different. So we've got 0's value 1, 0's value 2. So the result is 0. And if we go up the bits, bit 3, 1, yep, value 1. So as you can see there, doesn't matter if there's a bit set in any of the values, the result will be a 1. Great. So taking those, the same equation, we've got AB is value 1 and value 2 is F0. We find that we have set all of the bits in the upper nibble, making the result FB. And you'll find you need to do quite a lot of ORing in assembler as well. Now we're going to look at NOT. NOT is quite straightforward. It doesn't take two values, it just takes a byte value and it flips the bits on that byte and gives you the result. So if one is set in the input value, then the output value will be a 0. It is that straightforward. AB, and you flip all the bits, as you can see they're all opposites, and we get 54. Now this is XOR, and this is a little bit different, and how I tend not to use it a lot, but you will actually come across it, or needing to come across it, so it's worth putting this in. So what we do is in a XOR system, we say if any of the bits are set on the value 1 or value 2, then we say that the result is a 1. But if both bits are set to a 1, then the result is 0. Okay, so as you can see, if we go across here, this is a typical OR. So one bit is set on value 1, the result is 1. Same for 1. Look at number 2. Let's look at bit number 2. That's a 0. Bit number 3. Bit number 4. But when we come to bit number 5, we can see value 1 is 1 and value 2 is 1, and the result is a 0. So you see how it's switched that over. That is a XOR, and it's the same for bit number 7, the most significant bit, and that is the values that get switched there. So just to calculate these up, we calculate 1 plus 2 plus 8, which is 11. 11 in hexadecimal is B, and we've got on the upper nibble here bit 1, which is a 1, and a 4, which is a 5, which is set, so that's 5B. Okay, hope that wasn't too taxing. Assembly instructions: move, and, or, XOR, and NOT. So now we're going to look at a bit of assembler and then try this sort of stuff out. So if you've ever seen any assembler, you will see that it is filled with lots of move instructions. It's by far the most common instruction in assembler, and what it means is it means move a bit of data, as in a byte or a bit of memory or something like that, to somewhere else. So what we've got the move command, or the mnemonic I believe it's called, And then the size could be a byte, a word, or a long word, and that is designated by a B, a W, or a L. Then you've got the source operand and the destination operand. Now the source operand might be a number like 5B, or it could be a register, which we're going to cover, or it could be a piece of memory that is indexed by a register. And the destination operand could be a register, piece of memory, could be anything. Well, that is how the move instruction is actually set up. And if we want to take an example and move the value of 165 into the CPU data register 0, we can do it via any of these methods. Okay, so move.byte number 165, so that is denoted in decimal, comma D0, so that's data register 0. We can also reference it in hexadecimals by putting a hash and a $A5 D0, and that is going to set the number of bits to 16. Or we can move a long word, which is 32 bits, the value A5, which is 165, into D0. It's that simple. And which we've just covered, is similar in a sense of how it works in a source operand and a destination operand. Remember, AND takes two values, and if we want to AND the value F4 with value in D0, I'm taking F4 is 240 in decimal, so we've got AND.B 240, D0, F4 is 16 bits, 32 bits, real straightforward. Next we move on to OR. It's denoted like this, OR size, again source and destination. And if we want to OR the value F4 of F4, OR.B, OR.W, OR.L. So byte, word, long word. And EOR is slightly different how it's referenced. So XOR is slightly different. It's actually called EOR in the 68,000 CPU. Again, two values. So the source value, value 1, value 2, and that's how it's referenced. And we've also got NOT, and as I mentioned, NOT is just takes one value, so you just give it a source operand, and the result will be put in place. Not the value in DO, not .B DO, not .W DO, not .L DO. Okay. So what we're going to do now, after I take a swig of beer, let's take a look inside the CPU. And the best way to do this is to actually do it by an example. So here's a picture of MONAM. I spend a lot of time in this and lots of numbers, but we're going to look at these interesting parts here in MONAM, and we're going to actually fire up MONAM, and I'm going to just talk you through what these are. So it's going to come out of the presentation and fire up the virtual machine. Just create a little small program. Let's save that. Shift F10, which should be set up, and Shift F12. And there we go. So got a MONAM session running with the instructions that I had, and what we have is in the top left corner here, the 68,000 CPU has 8 data registers ranging from D0 through to D7, and these are 32-bit registers. As you can see, there's 4 bytes, 8 bits in a byte, and you can use these registers as you see fit. Now the CPU also has 8 address registers as well. You've got A0 through to A7, and you can use these registers also as data registers in some circumstances, but you'll use them as address registers. You'll see to the right of each address register where it's pointing to a place in memory. Now if we move across to memory. This is the memory of the Amiga here, and I'm going to come on to the memory map and things like that in a later episode. But basically it is pointing at bytes. So as we can see here, A0 is actually pointing to a place in memory. So if I just press M and point to A0, we'll see that A0 is C2, E4, F1, and it's given us a little insight into what bytes are actually stored at that memory address in memory. Okay, so we've got an A byte there, and that is the same for A0 through to A6 essentially. Now A7 is slightly different. That is typically used for something called a stack pointer, which I am going to come on to a bit later. There's the system stack pointer and user stack pointer. For now, we will typically not use A7. It's best to use A0 through to A6. A7 I will come on to because it's a bit of I need to cover that separately. SR, which I am going to cover now, is the status register. And the status register is really important for programming. And we're going to cover that in tri-states in just a minute. But essentially the status register, when we're executing instructions, and I'm going to just do an example now, we have this move quick number 0 into DO. I'm just going to run that instruction. The status register, based on what has been executed by the program counter, which is the PC here, and denoted by this little arrow, when we run an instruction, we will see that the status register is being updated. So we can see here that there's been some flag set, and that typically set the Z flag, which is the 0 flag. And when I updated D0 with the number 0, the status register set a flag called the 0 flag, and we can do tests on that flag and different things and branch to different things. So that's just wanted to explain how what the CPU registers look like there. So we've got the data registers here, address registers here, we've got the status register and its flags here, and we've got the program counter, which is where the actual program execution is pointing to. And that's typically what we needed to cover on that one. I'm just going to move into a bit more detail. So yeah, just as I've just covered that there, we've got, just to recap it, 8 32-bit data registers, 7 32-bit address registers. We've got the stack pointer, which is sometimes referred to as the USP or the SSP, the supervisor stack pointer, the user stack pointer for A7. We've got the program counter, and we've got these condition codes here, or the flags of the status register. And the flags I'm going to come on to right now. 16-bit status register, yeah. Okay, so these are the important flags in the status register, and we've got 5 of them. And when you execute an instruction, these flags may or may not be set based on what the instruction was. And I'm just going to cover these now. So we've got a negative flag, a 0 flag, an overflow flag, extend flag, and a carry flag. So I'm just going to give an example of an instruction that's being moved. So the result of the instruction was a negative value. So when I'm moved up B number $FF into DO, the result of that, as far as the CPU is concerned, is that it's a negative number. It's actually, from a byte point of view, it is -1. So if you had 0 as a number, and you said, and a byte has a maximum value of 255, which is what FF is. If you took 0 and said, right, on 0 and then subtract 1 from it, you would end up with FF. And on that basis, the negative flag in the status register would be set. And I want to show you how that actually works. We've got the 0 flag, and I just quickly covered that. The result of the instruction was a 0 value. So in the example I gave, was it moved up B number 0, D0. We've got a couple of instructions here, and I'm going to cover that. The result of the instruction caused an overflow. Moved up B number 100 was the first instruction in DO, and add up B number 30, DO. Now what this is, the overflow flag, is when the instruction has set the most significant bit, as in the last bit in the byte, it has set the overflow flag. Okay, so if bit number in a byte, bit number, if you go from 0 to 7, which is, so 7 is the 8th bit, if the 7th bit is set, it's flagged the overflow flag. So if we take 100 and add 30 to it, that's 130. The last bit in a byte is 128. That is the value. So therefore that bit must be set. So the value of 130 in a byte would be bit number 7, which is 128, and bit number 2, which would be 2. So 128 plus 2. We're going to look at this in a practical sense in a second with MONAM. And we've got the extend flag. So what the extend flag does is the result of the instruction caused exceeded the available bits. So it, as I just mentioned, the highest value of a byte is 255. Now in cases where you add a number to that exceeds 255, and in this case we're taking 200 and adding 100 to the byte. Now what's going to happen? It's going to the value of the byte is going to kind of loop round from 255 back to 0, and then adds, and then I guess the value would be well, the value here would be 45. Well, we'll have to check it in a practical sense, but basically because it's over 255, it's going to be higher. In that case, what the CPU does is it sets its extend register to say that the value is overflowed almost, or extended. It had to set the extend bit because the value doesn't fit into a byte or into the size of the bit size that you want, in this case a byte. And the carry flag is pretty straightforward. It's the same as the extend, but some are not affected by some instructions. So some instructions in the CPU will affect the carry flag, and some instructions in the CPU will affect the extend flag, and some will affect both. Okay, so we're just going to take a little look at that in a second. I'm first going to cover some MONAM basics. So in MONAM, I'll tell you what, I'm just going to load up all of these actually. I'm going to cover these. When we're in MONAM, we've got some keys here. So I guess you just use this as a reference slide. B to load of binary files, S to save a binary file, Control L to load an executable. We've got Tab to focus windows. We've got M to focus memory, up, down, page up and down in memory. And these are the important bits that we're going to cover now. In the program control, when you've loaded an executable file, typically what you're going to do is you're going to do things like setting breakpoints. You're going to be tracing the instructions. You're going to be skipping some instructions. You're going to be skipping over subroutines. You're going to be running entire subroutines, going into subroutines, and typically these are done with these commands here. Control plus T is a trace, which will execute the instruction where the program counter is pointing to, and Control Z is very similar, but the difference is that if the instruction is a BSR, which is a branch to subroutine, or a JSR, a jump to subroutine, typically it's going to actually go into the subroutine and start tracing those instructions. And we're going to come to examples of all of these. Control plus S is a skip. Control plus B is a breakpoint. So typically what you'll find is that as your code gets bigger, you typically want to set breakpoints and just run up until the program counter gets to that particular point in the code. And that's what a breakpoint is. Control and R to run your code. Control plus A is an auto breakpoint. I'll cover that. And Amiga key plus B is set breakpoint. And we've got some other useful things here. Amiga plus set R set register. Allows you to change the value of one of the registers, including the program counter in MONAM. And Amiga Key plus E allows you to edit memory, which is often useful. And you've got O to enter some expressions. So the enter expressions is really useful if you want to quickly calculate or see what the value of a hexadecimal number is in decimal or vice versa. You can use enter expression, and we'll show you that. Okay, so I'm just going to come back to this here, and I'm just going to go through the instructions on the AND, OR, and NOT and XOR, and I'm going to cover these status registers as well. So we're just going to quickly step back, and I'm going to cover. Just going to cover these here. So we've got an AND value. I'm going to write these up in the. In Notepad++. So this is how this is done. So we can come out of that for now, and what we want to do is just write a label called start, and we want to say, okay, we've got a value of move dot byte number dollar. What was the value? It was AB. So we're going to say AB, comma DO, and we're going to say and dot B, dollar FO, comma DO. And what I'm going to do is I'm just going to put a couple of knots here, okay? And I'm going to do the same sort of thing. Dollar AB, comma DO, and I'm going to say O dot B, number dollar F4, comma DO, and check what the values of those are. And I'm going to do a not again, and do move dot B, and the next one was a not. And we're going to do a not dot B, number dollar, and we're going to do a not DO, and we're going to do an XOR, move dot B, number dollar, AB, comma DO, and we're going to do an EO this time, dot B, number dollar, what was it, FO, comma D0, and not. So hopefully that should be pretty self-explanatory as to what I'm doing there. So we're just going to look at what we covered in the presentation. We're going to do an AND, we're going to do an OR, a NOT, and an EO. And hopefully I'm just going to save that, and hopefully it will compile. And it has. It compiled fine, as we can see there. And we'll just fire that up in MONAM. Okay, so as I mentioned in MONAM, to trace, so to execute an instruction, we're going to be pressing Control and T or Control and Z. Either will work. But I like to typically do Control and T. So we're just going to watch this D0 value here. At the minute it's 1, and we're just going to trace the instruction. Let's move AB into it, and we're going to AND that with F0, which is 240. And we'll see the result is A0. So as you can see from the presentation here, that value is A0. Go back to the virtual machine, we'll do O now. So we're going to move again AB into D0, just reset that, and we're going to do OR it with F0, and you'll see the value's been set now in D0 to FB, and you can see the value is FB. And let's see if we have a look at the knots. I'm just going to press the down arrow now and just focus things, so just trace it a little bit more and set the value to AB again. I'm going to knot that, and we get 5-4, and as we can see in AB, with all the values being knot, we've got 5-4 as the result, which is great. And again, and if we do the XOR with F0, we see the values went to 5B. So let's just check that. And as yet, fantastic. As we can see, the value is 5B there. Marvelous. So what we have now, if we just keep tracing down, what we're going to come on to is the status registers, which is what I wanted to cover now. Okay, so cool. We're going to just look at these, make sure that we understand these status registers here. And I'm just going to put these bits of code in just to ensure that we understand. So we okay to get rid of that. And what we're going to do is we're going to say move.b hashtag $0 ff comma do. Not. And we're going to say move.b number $0 comma do. Not. And move.b number dollar. Actually, it was 100, I believe, wasn't it? Let's have a look. It was 100 and add 30. Add .b number 30. Doesn't matter. 30 would do. And we're going to look at the extend flag as well, which I'm just going to type in move.b number dollar number 100 comma do, and we're going to add. Actually, that was 200, and we're going to add 100 to it. Now, you can use comments as well in Notepad++. You just put a... Sorry, I'm just getting lots of messages popping up here. Let me just quit my... There we go. Hopefully that'll stop. So what we're going to do is just run up MONAM, but I'm going to just show you how to put some comments in the code here. So this will set the negative flag and set the 0 flag and set the overflow flag. And set the carry flag. Okay, cool. So let's take a look at that. Compile it up. Shift F10, Shift F12. Oh, my wife has just won £300 at the bingo. Marvellous. I doubt I'll see any of that. Probably like go and wave it in my face or something. She'll kill us for saying that. Okay, so here we go. So we're going to just what we're going to be focused on here is what the SR status flags, the flags are set in the status register. So when I run these, when I do the trace, we're just going to see what status register flags are set. So when I do this trace here, and that has made, oh, yes, that has actually worked because the negative flag was actually already set. So as you can see there, we've got a little N, and that is the negative flag. And that is because the value that is being set has the most significant bit actually set, making it a negative value. Okay, so we're going to now do the 0 flag. And as you can see there, when I've run that, it's added a little Z, which is the 0. Okay, then we're straightforward. So now what we're going to do now is we're going to add 64 in hex, which is 100. And when we do that, you can see all the flags haven't been set. It hasn't set anything. There's not really anything interesting about that value. But now we're going to add 30 to that value, which is 1A. And I'm going to show you what the enter expression command does. So if we press O, and we want to work out what 1e is. Whoops, 1e. Say 130. It'll tell me it's 30. Press escape. But if we want to say 64 plus 1e, oh, I thought it would do that. Plus 1e. There you go. And say that's 130. Now what I'm expecting to happen here is the overflow flag to be set. Okay, so when I do the Control T, and there we go. It's set the negative flag, and it's set the overflow flag as well, because the more significant bit has been set, which is which is the value of 128 in the byte, but also it's overflowed into, and it's caused an overflow to set that, so it's set both values, it's set both flags. So now we're just going to do a similar sort of thing. What we've just set there, we'll just have a look. C8, that's 200, which is set the negative flag, as we can see, because the more significant bit is set. And now we're going to see if we can set the carry flag as well. So we're going to add to that 200, we're going to add 100, which exceeds the value of a byte, which is 255. So when we run this, and as we can see, we've got the carry flag which is being set, as well as the extend flag. Fantastic. Hopefully that makes sense. You'll also see that the value of DO has went to 2C, and it's went to 44. I think I said it was 45, but 44 is correct, because it's kind of wrapped around 255 and then had to add the where it would go up to 300. It can't exceed 255, so it adds the remainder to the byte, so then it ends up being 44. Okay, fantastic. So we're just going to keep back up with the presentation now, and so working with tri-states. So with tri-states, we use the flags of the status register to write some nice efficient code. When you're making a game, typically you tend to do a lot of this tri-states condition. You tend to do things like this three-way condition. You'll tend to do something like, right, do nothing, or start something, or stop something. So it's this three-way condition which I call a tri-state, which we tend to do a lot. And there's a really efficient way to do it, and there's a really inefficient way to do it. And I'm going to show you the efficient way to do it. So what we do is we look at the values of the status registers, and we have a test condition. So if you take on board that, if you take the value of D0, for example, being 0, okay, so the value of D0 has just been set to 0, and you want to do something based on that value. Well, what you can do is you say, right, we know that the status flags are going to be set, so you can say, right, the status register, we say, right, what is the value of D0, and then we check the status flags. We say, right, if it's 0, do something, enable a sprite. If it's negative, disable a sprite, or else just do nothing. Now, I've just got an example here of enable a sprite or disable a sprite. It doesn't matter. It could be enable something, disable something, or do nothing. And the way we do that is we use the test command, tst, assembler instruction. So we do test, then condition, and we say branch if equal, which is BEQ, enable sprite, BMI, branch if minus, that is checking the negative flag, disable sprite. But if if the BEQ is false, then the program counter then drops into the branch if negative, branch if minus, and that doesn't ring true. Then the only action left, which is this else here, is just do nothing. And this is a really efficient way of actually coding this tri-states this tri-states condition, and I use it all of the time in my games. So I'm just going to cover some branches and subroutines and labels. So when we're doing assembler, we have this we have what's called labels, and you can have global labels and local labels. And the local labels are really, really useful, and I'm going to show you what they are. So just taking the example of what I had there previously about the sprites, well, this is actually do something. So this is the assembler code here. So we come into this little routine here. So we've got do something, test the value of D0. Is it equal to 0? Was the status flag 0? That's what this BEQ does. Okay, then enable something. So what the program counter will do is it will jump to this global label. This global label here is typically, which we are code, is I put all my global labels in uppercase. So do something. Okay, so that's going to branch down into enable something. And then we'll have more code here. If it's negative, we'll have disable something. But otherwise, it's going to branch to this local label that we have here, exit. Okay. Now, when you're writing assembler, you can't have global labels of the same name. The assembler will, I guess the compiler will barf and say, look, I don't know. I've got two global labels of the same name. I don't know which one's which. But what you can have local labels, multiple local labels, but in different global labels, if you know what I mean. So in this do something routine here, I can have a .exit, which returns from a subroutine. Now I might have a do something else global subroutine with another local label with .exit, and that'll work perfectly fine. Subroutines, really easy. Might do something like this. If you've ever used BASIC, it's go sub or something like that, or I don't know. It's really common, but this is how you do it in assembler. This is just a BSR, stands for branch to subroutine. And what we've got here is do something, and the first thing that is run is BSR check something. So what happens is, as the program counter comes down to check something, it does something. And then this RTS here causes it to come back to the next instruction, which is this test.word size of D0. And then we've got, if the value of that was equal to 0, or set the 0 flag, and enable something, disable something, branch the branch to the local label, exit, and come back. Pretty straightforward. Okay, so we're going to check that out and just run quickly through that. So I've got the wrong window there, and we need to go into this one. So we're going to just scrub that. So here we go. So just doing these tri-states. So we'll just do tri-states example. And what we're going to do is we're going to say test.w this time, D0, branch if equal, enable something. If the negative flag was set, disable something. And if the nothing happened, we're just going to say branch .exit. So .exit is just going to be here, and we're just going to put a little knob in there. Now under here, we're going to create another global label. Say enable something, and what we're going to do is we're just going to set move 32-bit value number -1 into D7, and then we're just going to do I don't know, we'll do a return from subroutine, which should be fine. And similarly, we'll do disable something, move.l number 0, D7, and RTS. I'm just going to save that. But what we're going to do is we're actually going to here cause the condition. So we're going to say, right, move 32 bits long word, and we're going to set this to, we're going to cause this to disable something. So we're going to just set this to minus. We're going to force it to a minus condition. Okay, so what we're going to do, and just run this up. Okay, so in MONAM, again, we've got Control T to trace, and we're just going to set the condition. So we've set D0, the 32-bit value of D0 to -1, and we're going to test what D0 is set. And as we can see here, we've got the negative flag set, denoted by the N there. So first instruction here, the branch if equal to 0, which checks the 0 flag. Now that is not set, so that is not true. Now the BMI, which is branch if minus, that is the negative flag, that is true, so that is going to jump to disable something. So our program counter has jumped all the way down here. And essentially what's going to happen now is when we run this, we're going to set D0 to 0, and we're going to return, which is going to cause the program to end. Now, so that was an example of setting minus, and what we're going to do, we're just going to do the same sort of thing, but with 0. And if we just do move set D0 to 0, test it, and we can see there that the 0 flag is set. So this branch if equal is going to check that 0 flag. If it is set, it's going to jump to enable something, and indeed it has. Program count has jumped down. We set D1 to -1, and we're going to exit out. Great. Okay, so now we're going to cause it to do nothing. So to do nothing, we're just going to set it to 1. Set D0 to 1, and then that will cause nothing to happen, because the branch if equal will not be true, and the branch if minus, which is negative, will not be true. We set it to 1, and we do the test. So is the 0 flag set? No, it isn't. Don't take the jump. Is the negative flag set? No, it isn't. Don't take the jump. Got nothing else to do. The branch is just going to tell the program counter to just jump over, and there you go. It is just jumped to the exit local label, and it is ended. Now we can actually make this more efficient than what we have now. This instruction here, the move instruction, already sets the flags for us. So in essence, we don't actually need this test flag here. And we're just going to prove that now. So what I'm going to do, if you've noticed, I'm going to set that to -1. Okay. You notice the flags were already set. And if you see that, we have no test instruction now. Is the 0 flag set? Is the minus flag set, or the negative flag? Yes, it is. Take the jump. So by doing that, we've actually saved, from a performance point of view, about four cycles by doing that, because the previous instruction had already set the flags for us. So that should be pretty straightforward to work out. Okay. So we covered the global and local labels, we covered subroutines, and at the end of episode 2, if the confusion is set in, don't despair. As I mentioned at the start of this episode, I generally am around on Facebook, on Amiga Game Dev. Drop me a message. Drop me a message on Discord as well. I'm not on Discord typically during the day because I work full time. But you know, drop me a line. I generally get there on the night time around about 7 o'clock, 8 o'clock UK time. And yeah, and also as well, if you could like the video, I'd appreciate that. Or like the Amiga Game Dev Facebook page, or you know, just drop me a message what you do like about the video, what you don't like about the video. If there's anything you would like me to cover in the following episodes, you know, give me a shout and I'll be happy to cover it. So that's it for episode 2. Episode number 3 should be in about a week's time. I do have to go away for work for a few days, but I will try and get it in. We're going to be covering more assembler, and we're going to look at the Amiga's memory map and get into a bit more interesting things. But yeah, I'm kind of taking everybody from the beginning and taking them all the way through. You know, this is going to be a long-term project, I think at least a year, where I'm going to take everybody on the journey to making a game. So yeah, appreciate you taking the time to watch the video and hope you learned something, and I'll catch you in the next episode.